All right, hello. Let's take a look at problem 6. So, methane is stored under pressure in a 1 meter cube tank. The pressure in the tank is 20 bar and the temperature is 25 degrees C. So, first going through the problem statement, take inventory of what we have. All right, so we have a 1 meter cube tank. So, this is going to correspond to V total, my total extensive volume. The pressure in the tank is 20 bars. So we're told what the pressure is, and the temperature is 25 degrees C, so we're given T. So if I think back to Gibbs phase rule, if I have a single component, single phase system, I have 2 degrees of freedom. And so here, if we have a single phase system, since I've given T and P, my system's fully specified, I'll be able to solve the problem. All right, now going on to A. A, we're told calculate the compressibility factor of methane, that's Z, in the tank from the virial equation truncated after the second term. Use the value of the second virial coefficient provided at the end of the problem statement. So at the end of the problem statement, we're told at 25 degrees C, the second virial coefficient of methane is negative 4.22 times 10 to the negative 5 meters cubed per mole. Okay, so this has units of my molar volume, and so that's going to correspond to big B. Now, if you watched my posted lecture notes, when we think about the truncated virial equation, right, we can think of it as a power series expansion in P or a power series expansion in density, where density is 1 over the molar volume. Okay, both are equivalent. The form that's typically used in the book is my virial equation, my truncated virial equation is 1 plus BP over RT. Okay, and so really what we have here is this is my power series expansion in P, where I'm using my virial coefficient from my power series expansion in density. Okay, but regardless, right, it's BP over RT, where B has units of molar volume, so BP over RT is dimensionless, right, so long as my units are consistent. So in this case, if P and R say in SI units. Okay, the key is what I want you to get a feel for here is our virial coefficient, right, is typically we can only compute, 1 or 2 additional terms. So at most we have our second or third virial coefficient. And so you could think of it as a first order, or if you had that third virial coefficient, second order correction beyond our ideal gas equation of state. Right? For an ideal gas, Z is equal to 1. So the virial coefficient, its application is extremely limited. It's limited, or it's useful only when we have small deviations from the ideal gas equation of state. Okay, so the form that we'll use in this problem to solve is Z is equal to 1 plus BP over RT, which is the form used in the book. Okay. All right, so let's set up problem A then. Okay, so then the context of A, in terms of calculate the compressibility, so we use the form of our virial equation from the book. Our truncated virial equation is going to be Z is equal to 1 plus BP over RT. Okay, so again, my second virial coefficient, right, this term just accounts for a first order correction from my ideal gas equation of state, where Z is equal to 1. And so B has units of molar volume. Okay, my B term is negative, right? So Z, my actual Z is going to be less than 1, accounting for deviations from ideality. So now the main thing here is just when I apply this, okay, B is in SI units, and it's in units of meters cubed per mole. So when I solve, okay, I'm going to take P, okay, so P is equal to 20 bars. Okay, and I remember that 1 bar is equal to 1 times 10 to the 5 pascals. So 20 bars is equivalent to 20 times 10 to the 5 pascals. R, the only value I remember, is in SI units. So I'm going to use 8.314 joules per mole Kelvin. And then in terms of temperature, we're given the temperature in 25 degrees C, but I need to convert to absolute units, right? It's imperative that in essentially all of our thermodynamic expressions that we use absolute temperature, right? Exceptions will be if you have an equation such as the Antoine equation, where you're told, right, to use units of degree C. But in all of our fundamental thermodynamic expressions, we're going to need to use absolute units of temperature. So I need to convert from degree C to Kelvin. And so I do that by adding 273.15. So 25 degrees C is equal to 298.15 Kelvin. Okay, cool. All right, so now I'll go over to MATLAB in just 1 second, and I will compute Z. But I want to go and I want to set up B as well, and then we'll jump over to MATLAB and we'll solve A and B. So then B asks, what is the amount moles of methane in the tank? Okay. So the key here is that, okay, in A, I calculate Z. Once I have Z, Z by definition is equal to PV over RT, where V is my molar volume, right? So this would correspond to my actual molar volume. So solving for V, I get that V is equal to ZRT over P. Well, now if everything's in SI units, right, R is in SI units as I have above, T is in Kelvin, my pressure is in pascals, V is going to be my molar volume, and that's going to have units of meters cubed per mole. In the problem statement, we're also given V total, and V total is 1 meter cubed. So the link between the two of these is V is equivalent to, right, V is units of meters cubed per mole. It's equivalent to my total volume divided by the number of moles in my system. Okay, so we assume I have this homogeneous fluid, right? My molecules are equally distributed in that in my box. So V, the molar volume, is nothing more than the total volume divided by N. So if I solve for N, okay, N is going to be equal to V total divided by V, where V I just computed up here, right, based on my value of Z. So let's jump over to MATLAB and let's get numerical values for part A and part B. Okay. All right. So jumping over to MATLAB, sorry, I've got it here. Okay. So this is going to be problem 6. Okay. Oop. Boy, help if I open up a new script. So this is going to be problem 6. Okay, so in problem 6, okay, V total is equal to 1, and that's 1 meter cubed. Okay, so pressure, and I'm going to just convert it to pascals. Well, let's do pressure in bar. So P in bar is equal to 20. Pressure in Pascal. So my pressure is going to be my pressure in bars times 1e to the 5. Okay. Then my temperature in Kelvin. So my temperature in Kelvin was 298.15. Okay. And then the last piece was my virial coefficient. Which has units of meters cubed per mole, and B was negative 4.22 e to the negative 5. Okay, so B is equal to negative 4.22 e to the negative 5. Okay, cool. So then calculating Z. Okay, so to compute Z, so Z was equal to 1 plus B times P, where P is in SI units, is in pascals, divided by RT. Okay, so let me come back up here, and let's get our molar gas constant, R, and that's in joules per mole Kelvin. So R is 8.314. So compute Z. Z is equal to 1 plus BP divided by R times my temperature in Kelvin. Okay, cool. Let's see. I'll call this problem 6. Okay. So if I run this, right, Z is equal to 0.9660. Okay. So this is 0. Okay, so first, comment is in terms of, is the Virial equation of state applicable for this problem? Well, we get a z of 0.9660. Z is equal to 1 for the case of an ideal gas. So here we have a small deviation from that ideal gas behavior. So we'd expect that the Virial equation of state should be reasonable since we're very close to that ideal gas state. All right, so now let's calculate the number of moles. So first I'm going to calculate V, my molar volume. Okay, so let's compute my molar volume, and this is going to have units of meters cubed per mole. Okay, so V is going to be equal to, V is going to be ZRT over P. It's going to be Z times R times my temperature in Kelvin divided by P, which is in pascals. So my molar volume is 0.0012. Okay. So now to get moles, let's compute my number of moles. We said that N was going to be equal to V total, my total volume in meters cubed, divided by V. So I'm going to suppress V because we don't need its value at the moment. So now, we've got Z 0.9660 and N is 835.28. Keep flipping over. 835.28. So N is equal to 835.28. And so that's moles of methane. If you want to convert that to mass of methane, you just need to look up the molecular weight, which would have units of grams per mole, and you could convert from there. So we have A, and now we have B, the number of moles. Let's see what they want next. So now C asks, you want to store twice as much methane in the tank at the same temperature. What will be the pressure in the tank? Okay, so now in C, they're changing the problem up a little bit. So in terms of C, the temperature is still 25 degrees C, which is 298.15 Kelvin. My total volume is still going to be the same. My total volume is still 1 meters cubed. But now the number of moles, and I'm going to change this. I'm going to change my notation slightly. Let me call this, NC. The number of moles here in part C is 2 times the number of moles that I had here, which is going to be 2 times this 835.28. All right. So since the number of moles is changing, what else is changing is V. So VC, is going to be equal to V total divided by NC, where NC is 2 times the number of moles that I had earlier. V total over N, is just equal to my molar volume before. So my molar volume is going to be half of the molar volume I had before. So in C, we're told that my temperature is the same, but now we have twice as many moles in my same tank. So that tells me that my molar volume now in this part C, where I have twice as many moles, so the number of moles is twice the number of moles I had before. So my molar volume is half of what I had before. So VC, my molar volume in part C, is going to be half of V. So now I know V. So I know T and I know V. So again, if I have a single phase system, and I'm going to have a gas phase, I calculated Z that was close to 1. So if I have a single component single phase system, I have 2 degrees of freedom. So here now I know T and V. So my system is specified, it's fixed. So now it's just a matter of working with it and solving. So let's see what we can do. So we know T and V. So the question is, can I calculate P? Or how can I calculate P? Okay. Well, so if I go to B, right, what we were working with is we had our definition of my compressibility. So Z was equal to PV over RT. And then we had our compressibility equation in A. Z is equal to 1 plus BP over RT. Okay. So from up there, let's see. So if I look at part B, so I don't know Z. So Z is unknown. So unknown 1 is Z. Unknown 2 is P. Okay, but I know VRT. If I look at A, okay, I don't know Z and I don't know P, right? But I know B, R, and T. So essentially, this gives me two equations with two unknowns. My two unknowns being P and Z. So I should be able to solve for Z and P. So let's see if we can do this. Okay. So the key is going to be okay, truncated virial equation tells me Z, okay, and I'll call this ZC, right? Z from part C is equal to 1 plus B P, I put a superscript C on there, over RT. Okay. RT and constant are the same. And then my definition of Z is ZC is going to be equal to PC VC over RT. Okay. Cool. All right, where VC I could replace with 1/2 V, but I'm not sure if that's going to get me anywhere, so I'm just going to leave that as it is for now. All right, so now I could go in either direction. I could plug this in up here, or I could plug that in here. Either way, it's going to give me an equation with a single unknown P. Okay, so let's plug this in here. So now I have P C VC. Okay, just tell me this is different for part C than it was for A. PC VC over RT is equal to 1 plus B PC over RT. Okay, let me see if I can solve for P. So I'll bring this term over here, and so I end up with PC times VC over RT minus B over RT is equal to 1. Okay, so PC is equal to 1 over, and then I could even factor out the 1 over RT, 1 over RT VC minus B. Okay, and now, VC was just 1/2 V. So PC is going to be 1 over, okay, did I do this right? Yeah, 1 over RT. So actually I could bring RT up here. So, because that's 1 over RT. And then this becomes, well, VC is just 1/2 V minus B. Okay, so I should have that PC is equal to RT over 1/2 V minus B. Let me try it again. 1/2 V minus B. Okay. All right. So now, I guess as a quick sanity check, so we expect as I add more to my tank that the pressure should increase. Okay. So if I look at this, is if we were to, solve or rearrange our equations as we had in part A and B for our original system, we'd have P is equal to RT over V minus B, right? As I had VC here. So now, though, VC is being replaced with 1/2 V. Okay, and so I expect my denominator is going to become smaller, right? Because this is 1/2 V. The negative B, well, B is negative, right? So this term's positive. Okay, so this denominator is going to be positive, but it's going to be smaller than I had in A and B because now it's 1/2 V. So the denominator is going to decrease. So I'm dividing by a smaller number, so the quantity should increase. Okay, so it should work out that my pressure should be greater. Okay, so let's jump over to MATLAB. Okay, so PC in the second case. So I'll call it PC. And so it's in pascals initially. So PC is equal to, we had R times T divided by 1/2 V minus B. So I'll do 0.5 times V minus B. Okay, and then I'm going to, just for completeness, pressure in part C in bars. So PC in bars would be PC divided by now 1e to the 5. Okay, so running, it's because I call this T in Kelvin. So now running, okay, there's my pressure in pascals. Then converting to bars, it's 38.6829. Okay, so my pressure in C is 38.6829, and that's bars. Okay, and just as a note too, as a sanity check, is if my system obeyed the ideal gas equation of state. Right, so if I had an ideal gas, then PV equals RT, or PV over RT is equal to 1, right? My compressibility is 1. Instead, be PV over RT, okay, would be equal to PC VC over RT. Okay. So this is if I had an ideal gas. Okay, and so if that's the case, well, we showed that VC was equal to 1/2 V. So this would be PC over 2 times V, right? Because VC is 1/2 V. So if that was the case, then PC, okay, then I can cancel V. PC would just be equal to 2 times P, which would be 40 bars. Okay, so for a real system, it's slightly less than double. Okay. So a quick sanity check. So that's C, that's how we would compute the pressure if we were to double the number of moles. Then is it appropriate? So again, when I think about virial equation of state, okay, so this is a first order correction from my ideal gas equation of state. For an ideal gas, Z is equal to 1. So I have a first order correction from ideal gas behavior. So if I look at A and I have a Z of 0.9660, I am pretty close to ideal gas behavior, right? My Z is pretty close to 1. So since I'm pretty close to ideal gas behavior, I expect the virial equation to be reasonable. Just for completeness, if I were to look at, C, Z in part C be 1 plus B times P divided by R times T Kelvin. Okay, so in C, now Z's 0.9341. So I'm getting further away from an ideal gas. All right, so in A, I'm pretty confident that I'm pretty close to an ideal gas, so virial equation should be reasonable. In C, I'm not as confident, right? I'm getting further and further away from that ideal gas equation state, so it's becoming more questionable as to whether or not the virial equation is applicable. Okay. In reality, I'm not sure that I've ever used the virial equation of state. So NIST has virial equations for things like helium parameterized. They have a large number of terms, say 10, 20, 30 terms in their that have been parameterized for some of these gases, which they use as reference fluids for calibrations. Okay, but otherwise, for practical applications, you'll probably never use the virial equation of state. You'll have better luck using a cubic equation. But the goal here is to give you an illustrative example of working with the virial equation. So I hope that helps. If you have any questions, by all means, please just let me know.